Picture yourself at the turn of the 20th century. Classical physics is riding high. Newtonian mechanics explains motion. Maxwell's equations describe electromagnetism. Thermodynamics governs heat. Scientists thought they had the universe figured out. But then came the anomalies. And the biggest one, something as simple as a glowing piece of clay. Ancient artisans had known this for millennia. Heat clay in a furnace at high temperatures and it glows. First red hot, then yellow hot, finally bluish white. You see the same thing with candle flames. It's one of the most basic observations in nature. Physics thought explaining this would be trivial. After all, physicists understood the pieces. Heat is just atoms in motion. The hotter something is, the faster its atoms move. Atoms carry electrical charges. When you move a charged particle, it radiates electromagnetic radiation according to Maxwell's equations, and the color indicates the frequency of that radiation. So, they applied Newton's laws to the atoms and Maxwell's theory to the light. They did the calculation and the answer was impossible. According to their math, the energy emitted should become infinite at high frequencies. This became known as the ultraviolet catastrophe or the Rayleigh-Jeans catastrophe. Classical physics had hit a wall. In his book, The Structure of Scientific Revolutions, Thomas Kuhn describes exactly this kind of moment, when the prevailing paradigm can no longer explain the observed phenomena. We were witnessing the birth pangs of a new era. Enter Max Planck. In 1900, while preparing material for his physics class, he tried a strange approach, not because he believed it, but because it worked mathematically. What if energy wasn't continuous? What if atoms could only emit energy in tiny discrete packets? It seemed absurd. But when Planck ran the numbers with the assumption, something remarkable happened. He got the correct curve linking frequency and energy for light. To make this work, he introduced a new constant, h, now known as the Planck's constant. This number is incredibly small. In fact, if you set h to 0, you are back in the Newtonian's world. But that tiny number would change everything. Planck himself didn't fully believe his quantum hypothesis, but Albert Einstein did. In 1905, Einstein explained the photoelectric effect by taking Planck's idea seriously. He proposed that light itself comes in discrete packets, particles he called photons. Light had a dual nature. It could behave as both a wave and a particle. This was revolutionary. For centuries, we had debated whether light was a wave or a particle. Einstein said it's both. In 1924, a young French physicist named Louis de Broglie asked a simple but profound question. If light can be both particle and wave, why not matter? If electrons, atoms, or matter also had wave-like properties? This leads us to one of the most mind-bending experiments in all of physics, the double-slit experiment. Imagine shooting photons one at a time through two slits towards a screen. If photons were simply particles, you would expect two bright bands on the screen, one behind each slit. But that's not what happens. Instead, you see an interference pattern, alternating bright and dark bands. This is the signature of waves interfering with each other. But here's the crazy part. When you are sending the photons through one at a time, each individual photon somehow knows about both slits and interferes with itself. When you try to measure which slit the photon goes through, the interference pattern disappears. The act of observation changes the outcome. This isn't a measurement error. It's fundamental to how nature works. One of the Schrödinger's colleagues posed a challenge. If matter acts like a wave, what equation does it obey? In 1925, while on vacation in Alps with one of his girlfriends, Erwin Schrödinger came up with his famous equation. This equation would overturn the prevailing model of the atom. Before Schrödinger, Ernst Rutherford had proposed atoms were like tiny solar systems, point-like electrons orbiting a nucleus. But this model couldn't explain the structure of atoms or why there were so many different elements. Schrödinger's wave equation provided answers, but it raised a disturbing new question. If the electron is a wave, what exactly is wave? Max Born proposed an answer that split the physics community down the middle. Matter consists of particles, but the probability of finding that particle is given by a wave. This interpretation created two camps. One team, Planck, Einstein, de Broglie, and Schrödinger, who believed there had to be some underlying reality behind this. And the other team, comprising of Niels Bohr, Werner Heisenberg, impressed the probabilistic nature as fundamental, which constitutes the Copenhagen interpretation. The Copenhagen interpretation gives us a simple recipe for quantum mechanics. Start with the wave function, insert the wave function into Schrödinger's equation. The wave is a superposition, a sum of all possible states existing simultaneously. When you make a measurement, the wave function collapses to a single state. Step 3 and 4 are where things get controversial. Step 3 says that in the subatomic world, an electron can exist simultaneously in multiple states. Note we don't know which state it is in. It's literally in all of them at once. This is impossible in Newtonian mechanics. Step 4 says that only when you measure does reality crystallize into one outcome. Before measurement, there is only probability. Einstein hated this. God does not play dice with the universe, he declared. Bullshit back. Stop telling God what to do. Schrödinger himself tried to show how absurd this interpretation seemed by proposing a thought experiment we now call Schrödinger's cat. Imagine a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers, breaking the vial and killing the cat. If it doesn't decay, the cat lives. According to quantum mechanics, until you open the box and observe, the atom is in a superposition of decayed and not decayed states, which means the cat is simultaneously alive and dead. Schrödinger meant this as a criticism. Surely cats can't be both alive and dead, but quantum mechanics says until you look, they are. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper challenging the quantum mechanics. They describe what you now call quantum entanglement, where two particles become correlated such that measuring one instantly affects the other, no matter how apart they are. Einstein called this spooky action at a distance and argued it proved quantum mechanics was incomplete. But experiments have since confirmed entanglement is real. And this spooky phenomenon is exactly what makes quantum computers possible. I know this sounds crazy. Einstein, the greatest physicist of the 20th century, thought it was crazy. But here's the thing. Quantum mechanics work. When we use quantum theory to predict properties of electrons and photons in quantum electrodynamics, the predictions match experimental data to within 1 part in 10 billion. It's the most successful and precisely tested theory in all of science. Whether we understand why it works or not, nature follows quantum rules. And now we are learning to harness those rules to build quantum computers that can solve problems classical computers never could.